I truly want us to live in a world 50 or 100 years from now where people are jumping in their rockets like the Jetsons and there are families bouncing around on the moon with their kid in a spacesuit.
The Interplanetary Podcast. The exploration of space. For the benefit of all humankind. Your host, in Guildford, England, Matthew Russell.
Oh yeah, Jared Isaacman. Yeah, so that was a quote by Jared Isaacman. If you don't know, he's a tech billionaire, something to do with finance and stuff, who's been up to space twice now as a private passenger on board a SpaceX capsule. But he's likely to become the new boss of NASA, which will be very, very interesting. I'd love to see how this pans out. I'd love to hear your opinion on it. So you could, of course, join me on Discord by going to the Interplanetary Podcast Patreon site. That's patreon.com/interplanetary, and joining in for free there and maybe joining up and coming on the Discord and having a little chat about lots of all the different things that we talk about on the show. So, talking of Patreons, I must thank Justin Roberts, who's been there for ages as my Uber patron. Thanks very much, and I shall be mentioning some of the other legends near the end of the show. So, before we go to our space radiation interview, a couple of British space newsy things I thought I might as well talk about, and that is, of course, Orbex, who Jamie and I visited when they first announced Prime. They have decided not to launch from Sutherland for a while and pivot to the Shetlands, and I believe there's a little bit of speculation that might be because they're going to abandon Prime and go for something slightly bigger called Proxima, as a medium kind of lift vehicle. But let's see what happens. Do we believe that there's going to be a first launch in 2025? If there is, that'll be very, very exciting, but it always seems tantalisingly close. And of course, the other really sad news that happened, again, a sort of one that's very much associated with the podcast, and that is Alan Bond's project, the Sabre engine. Skylon long gone, of course, but the Sabre engine now is, of course, officially gone and bust, with Reaction Engines not being able to get the funding for their engine. Now, is that because it is a dead end, technological dead end, as SpaceX with their recoverable boosters just means there's no call for space planes? That's another thing I'd like you to talk about. Send me your opinion on. I really just don't know. I find it quite hard. Will there ever be space planes, or are reusable boosters the technology now? That's that. Now, one thing I was really excited to see is the European Southern Observatory's extremely large telescope, the ELT. That's looking pretty good. It's the construction of it is getting ahead, and you can actually go and see some pretty impressive pictures of the structure. So, yeah, no first light until 2028, but it's looking like a reality in Chile's Atacama Desert right now. So that's exciting. And of course, congratulations to everyone over at Arianespace and Avio. Some really great people that have managed to get the Ariane Vega C successfully flying again. That's good to see that European space launch is back up on its feet a little bit. Right, we know that one of the biggest problems in space exploration is radiation. How do you get around it? And of course, it's not just humans that suffer from radiation, but of course, electronic devices. When that gets hit by radiation, it can flip bits or destroy the circuit altogether, and so computers stop working, etc., etc. So it's a really, really big problem in space exploration and with satellites and with Earth observation is radiation. So my next guest, Yanni Barghouty, he is the CEO of a company called Cosmic Shielding Corporation. They seem to be developing a solution for some of these problems. And this is my interview. Écoutez.
The Interplanetary Podcast is
alive! I am joined on the podcast by Yanni Barghouty, who is the CEO and co-founder of Cosmic Shielding Corporation. Welcome to the podcast, Yanni.
Oh, great to be here. Thank you, Matthew.
Let's have a little bit of background, Yanni, about yourself, because the conversation is going to be based around your company that builds shielding, and we'll get into kind of AI in space as well. But give us a little bit of a background about how you kind of found yourself in the space that you're in.
So definitely, I had a little bit of a cheat code to get into the space industry, and the fact that my family, their entire family is physicists, nuclear physicists and astrophysicists, right? So they're theoreticians, so not really on the applied side, but I kind of grew up in that environment. My dad actually did a lot of work with NASA, does a lot of quantum physics, applied quantum physics in some cases, which is, a new thing now. My mom was a radio astronomer, actually, so lots of the really out there stuff, looking at quasars, cosmic microwave background, etc. Now, I have a background in biomedical engineering, but our co-founder, Dr. Lembit Seaver, has been a family friend. And, we really got into this because he was visiting. I was working at a previous startup, ended up leaving, working with one of our VCs, actually our main VC, and kind of got bored of it, wanted to get back into creating things. And I was talking to Lembit, we were talking about the space industry. This was back in like late 2020, talking about how pretty much under everyone's noses, there was so much happening in space, right? People didn't realize just the sheer, aside from what they hear about SpaceX, how much actually was going on in terms of new systems, new launches, et cetera, et cetera. One thing we noticed, though, is that the way spacecraft were built, so the most satellite buses, hasn't really changed fundamentally in a long time, decades, right? The types of systems we put on board has been changing, right? Like we're using more modern electronics, novel systems for like robotics, et cetera, et cetera. But the fundamental materials haven't really changed. And one of the things that we noticed was, look at SpaceX, with the Starship. They were using a steel frame for the Starship, and their goal is to get to Mars eventually. And, I'll talk about this later, but one of the things we knew was we were joking about how that's going to kill your astronauts, given enough time, right? Because the thing with heavy metals in space is they actually make the radiation environment a lot worse, So then we started getting into solutions. And, Lembit's, of course, just to give you some background with him, he's been doing this for decades. So he's led radiation mitigation strategies for ESA, JAXA, NASA, worked with NASA SRAG, that's the Space Radiation Analysis Group. In the past, he actually developed some of the fundamental physics models that are used in a lot of the simulation systems that are used by NASA and JAXA and ESA, like FITS, the particle heavy ion transport code system, GEON4, and so forth. So we had an idea of what we wanted to make, but looking at, essentially the ecosystem, I just thought it was the perfect timing. And I was like, Lembit, with kind of his background, it's academic integration. We worked a lot, pretty closely with the MIT Polymer and Materials group called the Borskina Lab initially. I was like, this is a no-brainer. This is something that can have a significant impact in, one, the sustainability of space and the performance and capabilities, and then eventually human exploration. Because, of course, everyone's excited by human exploration. But yeah, that's really how we got into it.
Well, yeah. So, yeah, you're kind of almost destined. You couldn't not be into it, right? Well, yeah. with that kind of background, I mean, yeah, you look sickeningly young to be a CEO of a company. So I'm already annoyed.
Yeah, it's funny because that I've noticed. My previous startup was in the software space, and no one cares how old you are in software. With space, though, until very recently, it was, you had to be seasoned. You didn't see any Silicon Valley-esque, startups with young founders coming into play. But yeah, no, it's good. I mean, I'm proud of where we've gone so far, and it's finally working out. So that's the exciting part.
Yeah. So obviously, you have a technology that puts you unique. So can you tell us a little bit about the technology behind the company and why that is different from what other people are up to?
Definitely. So I'll start off with why radiation is even a problem in space, because that's a bit, since we since the Apollo era, we've known this is a concern. Funny enough, actually, there are solar storms that we've seen in very recent past, like we're talking months, that purely by chance, if the Apollo astronauts were up near the moon around the time where a storm like, the recent ones occurred, happened, they would have died, right? So there's a lot of luck involved in early space exploration, as usual. So with radiation in space, right, it's not like when you look at X-rays or gamma rays, right, you think of using lead to protect against it, right? It's actually particles. It's particles from the sun, protons that are being thrown out of the sun during, coronal mass ejections and other solar particle events. And then you have cosmic rays. Cosmic rays are actually particles as well, like, but actual things like iron-26, right, actual elements being thrown out of supernova, right? They have a lot of energy, needless to say. Same with the protons. So instead of thinking them out like waves, like X-rays and gamma rays, you're talking about little bullets going at near the speed of light. So they're a lot harder to shield against than things we usually deal with on the ground. So what they do is once these particles hit a target, whether it's in a computer, say transistor, or a DNA strand, right, they can actually destroy the target, right? If they don't destroy the target, they have a high probability on a transistor, as an example, of imparting enough energy to cause the bit to flip. So it was a 0 and now becomes a 1. And sometimes vice versa if it causes any weird charge buildup in other areas and causes these odd errors to occur. So over time, that actually makes a system inoperable, right? Not just from failure because it's so damaged, but actually on the day-to-day, you get so many errors that you just keep getting blue screens, essentially. It just keeps resetting. Cameras, right? Cameras have the same problem. Over a long duration, the pixels actually start basically dying out. You start getting stock pixels, dead pixels, all of CCD. So the way we used to work around this, and still do, is using radiation-hardened electronics, right? So that basically is, there's many ways to do it, but the principles generally are you have transistors that are larger, sometimes made out of different material in very expensive and extreme cases. They're spaced further apart so that a collision is less likely to damage adjacent transistors. And they triple them up, right? They not always triple, but they put redundancies in place. And they check to see that each one is getting the same calculation so they can catch errors, right? Another option is that they send the same signal 3 times over, right? And just how it sounds like that would reduce your computing power, right? Pretty severely. And it does. It's the opposite of Moore's law, is essentially what we're doing to electronics in space. So realistically speaking, honestly, like most satellites, people think of space technologies, there's some crazy stuff, and there is, right? But the computers are not part of that. A lot of them have the performance of maybe a desktop computer from 25 years ago, 30 years ago, right? The smaller the transistors get, the more vulnerable they get to radiation. So then that makes the problem even worse. But then what started happening in space is that we wanted to do, higher resolution images, right? We want to get real-time processing of images. So we're not sending down pictures of cloud 70% of the time, right? On-orbit refueling and on-orbit servicing, right? They need cameras that have advanced docking procedures built in, like machine vision, right? And good integrations there, robotics, right? All of these things require more throughput, more compute power than we have been able to use in space. So the idea of that, if you're able to soften the radiation environment through shielding to the point where you can use these modern electronics, you could do wonders for the operators in space. All of a sudden, not only do you extend the lifetime of a satellite from maybe 2 to 14 years, which not everyone cares about just because, they're going to refresh it at some point within that. But now all of a sudden you increase your compute power by orders of magnitude, 100 times, 1,000 times. If you're talking about AI, it goes crazy because obviously, you need specialized hardware. Speaking of AI, parallel architectures, so graphics cards, right, GPUs, are even more vulnerable to those radiation effects because they're working in parallel. A single error has a significantly higher chance of cascading into a bunch of problems. So that's the main reason radiation's a problem in space. It's how it affects the electronics, right? Then there's charge buildup, over time, you have just energy building up on the systems. Think about it like that, can cause arcing and so forth. And then there's the human spaceflight side. Now with people, it's a big problem too, right? As you can imagine, they're just as vulnerable. Those manifest in DNA strand breaks, maybe damage to your rods and cones in your eyes, right? Effects on the brain, which is actually I think, a little understudied, but it is a concern that over a long duration space mission, you might actually have induced Alzheimer's or dementia, like on a Mars mission, just because of the collisions of the brain. And an interesting case is if you talk to any astronaut, right, they'll mention that when they try to go to sleep in space, they see flashes in their eyes, right? Like when their eyes are closed, they just see flashes. Those are actually collisions of these energetic particles with what they originally thought was just the rods and cones in their eyes, but it's actually also hitting their brain and causing them to essentially process a flash, right? Ugh. It's a little scary stuff, right? And there's still a lot of work to be done in understanding what are the long-term effects of all these things. It's not just cancer people are worried about, it's these other effects. But that's another area where, again, shielding becomes key. So now, instead of a 6-month duration mission that would be within a kind of realistic, say, radiation lifetime exposure limit for an astronaut, like on the moon, right? We can get to maybe 15 months to 5 years for a lunar, maybe even longer if you have a very robust shielding configuration, right? Maybe 10 years. So I think now that we're moving into this kind of permanent presence in space, rather than just a few communications and imaging satellites here and there, it's becoming increasingly critical. And the last point is those radiation hardened electronics, the previous countermeasure. They're very expensive, right? A little flight computer that maybe is like a cell phone from the early 2000s in terms of power, right? Processing power might run you $1 million, right? That's not unheard of at all. That's kind of commonplace, actually. A little integrated circuit, like maybe even like batch controlled, like resistors, capacitors, all these little components used for manufacturing, they're hundreds of times more expensive than the off-the-shelf part. Not only that, they're not made in volume, as you can imagine, right? So the sheer number of satellites being launched up, even Starlink is a perfect example. There is not enough supply of radiation-hardened parts as it stands to be able to fulfill the demand of satellites like that. Now they're going the route of using, disposable satellites, so to speak. But as the industry is growing, it's becoming a serious problem. They don't want to wait 12 months to get a part to be able to manufacture a satellite. They want to use what's readily available. And, the space electronic industry is never going to compete with the Earth electronic industry. Compared to that, it's a very small piece. So tapping into the terrestrial supply chain there is key.
Yeah, I mean, I hear this time and time again on the podcast. This kind of off-the-shelf components is really where you want to go, because the savings just phenomenal. Actually, I was talking about the music industry earlier on. It's exactly the same. We use networked audio. Imagine trying to do that. If it was just designed for the audio industry, it'd just be far too expensive. But
exactly.
So we piggyback on off-the-shelf stuff. So it's a common theme. But the way that you outlined the problem of these protons and ions traveling at almost relativistic speeds and with just so much energy, it's ridiculous, unstoppable, really. And it just seems like you're going into this incredibly harsh environment, and it almost seems like, well, how would you go about trying to stop this? So presumably you've made some headway in cracking that nut, as it were.
Absolutely. And part of it, funny enough, is, I wouldn't say luck, but there were a lot of engineering traditions that were being implemented from the shielding standpoint that were based on old physics from like the 80s, right? Which actually led to people using shielding materials that they shouldn't have been using, right? So that gave us a little bit of a window. And also there's some new physics, old physics that makes that, really makes this clear how you can make an effective shield. It's not magic. So what essentially we did, we have a nanocomposite polymer. We developed this proprietary polymer, and we have a matrix of nanoparticles that's dispersed throughout it. One of the tricks in manufacturing is how to make sure that matrix stays somewhat uniform after you extrude it, 3D print it, injection mold it, etc. Honestly, that took way more time than getting the formula. Way more time. I'd say 90% of our efforts were on that, not the formula. Because the formula, if you have the physics background, you have an idea. So think about it like this. These particles have, to your point, they're insanely energetic, right? You're not going to stop all of them. That's, for now, impossible. Maybe one day when we have micro fusion reactors and energy shields, sure, maybe we'll stop all of them. But for the time being, what you can do is reduce how damaging those particles are. So I mentioned earlier that metals can be a problem, heavy metals, right? The reason that's the case is when these protons or heavy ions, when they hit a target, they have a chance of causing this target fragmentation. So they literally break it apart. It's like essentially the actual structure. You have protons and neutrons flying off, right? Also, you have the release of X-rays and gamma rays, right? Even if you slow down the particle, what happens when a particle that's going at relativistic speed slows down? It releases a huge amount of energy in the form of X-rays, right? So essentially what you want to do is reduce as much as you can the energy of the main particle, right, with something that has a low chance of causing fragments to be released. So hydrogen theoretically would be the best, right? That's why you might have heard water, right? The idea of using water as a shield has a decent hydrogen content. Pure hydrogen would be better, right? But then when that occurs, one of the things that I think was sometimes overlooked with the water approach is you want to be able to capture these secondary neutrons, these X-rays and gamma rays that are being emitted during that process. You want to also capture those. And at the same time, another problem with water is it's hard. How are you going to engineer water around the satellite, right? That's a bit of a headache for an engineer who already is pretty stressed about the entire mission, right? Then we put in a bunch of other stuff to make it essentially strong, physically strong, thermally conductive, as much as you can really get with plastic, right? Because it's essentially an advanced plastic. So we took in that holistic approach. So essentially what we end up doing is we don't stop all the protons, but once the ones that manage to get through, the amount of energy they're able to impart on the target actually can be low, right? And they call this the LET, the linear energy transfer. Usually there's a certain threshold at which it's sufficient to cause either destruction of a target or a flip a bit. So it's a distribution. Some of the particles get through, some of them are totally stopped by the shield at lower energies, and then a certain chunk of them make it through. The ones that make it through are reduced in number on average, but really it's the damage potential of those protons and heavy ions is reduced a little bit to the point where you actually see measurable effects. So one of the more exciting things is we finally got back some really, to me, is the more exciting results from the NVIDIA mission that we launched a couple months ago with Aethero. And then we did the largest in history test of radiation screening of COTS electronics ever, right? We characterized about 40 NVIDIA Jetson ORN boards, the NX and AGX, so the small and big one. And we did this at particle accelerators across the world. So Triumph is a proton neutron accelerator, NASA Space Radiation Labs, and then HIMAC Heavy Ion Medical Accelerator in Japan. And we were able to actually see that the effects of what I just described on electronics, and it was in line with what we saw on detectors and other systems in the past. We are able to cut the error rates down by about an order of magnitude, roughly 8x, sometimes higher, sometimes slightly lower, and directly have an effect on the lifetime of the system as well, proportional to that reduction. So prior to this, we've had a lot of demonstrations, lots of other accelerator testing, but this was really exciting because it's a really hot commodity. This NVIDIA system everyone wants to use. Everyone used to think these errors would be the death of it, right? And they would have been. But yeah, we showed the application of that physics. So essentially what it's doing is, as I mentioned, making the problem a little less bad, right? By mitigating the secondary effects and doing as much as you can do to mitigate the primary effects.
So that's enough, is it, to then open the door to products and technologies that previously had kind of been shore-bound because they just weren't robust enough to be able to go in even a modern spacecraft? They just...
Absolutely.
So presumably that's where it's going now. You're able to do the next. I guess the next step then is to start with your radiation shielding is to then be able to, I guess, almost launch a whole kind of new paradigm in space, which is things like AI. So am I right in saying that? And
Yep.
In which case, where do you see that going in the near term, and where do you see it going in the sort of far term?
Absolutely. So yeah, you hit the nail on the head, right? It is kind of trying to enable that shift in, I call it payload flexibility, just unlimited payload flexibility. No longer do you have to, spend months trying to do batch control on certain parts. Like you just design the system you want to design, right? So we did finally demonstrate too, with real examples, that it works, right? We did this on orbit, on the ground, many times over. And what this now allows is you can go to NVIDIA's website and get an evaluation kit for one of their systems on a chip, right? Or their modules, right? And you can get it to have the same lifetime expectancy in LEO, say like even like 1,000-kilometer orbit, like as you would a $100,000 radiation tolerance FPGA. All right, that's a big deal. Now all of a sudden you are enabled. So right now, the application that we're seeing the most of is the idea of optimizations almost, right? Being able to have faster processing on board allows them to, the customer, right, the satellite operator, to integrate more robust services, whether it's higher resolution imagery, right? More advanced sensors, like being able to process all that incoming information at once, better maneuvering, right? Like real-time avoidance of debris, right? Say like in the future, that's actually not in the future, this is about to be a thing, or on-orbit service. One area that I think is coming potentially, right? I still have my own reservations about it. I'm not from a technical standpoint, but more from a, I want to piss people off, but from a business standpoint, is data centers in space, right? So the idea of in-space supercomputers, it makes sense, right? And we have now shown that you can use the hardware you need to make that possible in space. One of the barriers I think that still exists there is the power generation, right? Even though the solar power is very efficient, right, in space, much more efficient than on the ground, we can't shield solar panels easily. Yeah, we can do the backplane shielding, but it's still only doing like a 50% job there. So that's the next nut to crack in order to have in-space data centers. But I think that is coming. I think that is coming very soon. And then even further in the future, right? We're talking about maybe long-duration missions for astronauts. The Lunar Gateway project. We are actually working with some companies that are developing technologies for the Lunar Gateway. On transit to Mars, right? That's I think still there's a lot of legwork to do, but what essentially this is allowing us to do is lay the infrastructure to make that possible, lay the infrastructure sustainably too. A small piece that I always think is worth looking at, but I guess from not many tend to appreciate it as much, is debris in space. A lot of these little mega constellations, that the satellites they use in mega constellations, they have very short lifetimes, right? And the amount of debris now cluttering up the Earth orbit, right? And that's what it's about to become over the next 10 years. Now that we're having constellations of thousands of satellites, that's a big problem. We want to make sure that we don't have to throw away a satellite every year, right? So that's another application why I see it has a benefit for everybody. But yeah,
it's fairly obvious, isn't it, that increasing the lifespan of expensive big machines is going to be ecologically sensible thing to do, right?
Exactly.
I know there's recent reports about like just allowing satellites to burn up in the atmosphere is not particularly helpful for the atmosphere's health. So it's like, that totally makes sense. If you're basically saying that the shielding not only allows you to take more powerful stuff up, but it also allows you to take the normal stuff up for longer, presumably. Yeah. So. Yeah, I mean, we could the data center one. I can see why the reservations with data centers and things like that. But presumably the reason why that's even a thing is because it's cold in space, because you can keep these things at a cooler temperature, or what is it? What's the advantage that is? Because you can see what the disadvantages are, but why is it an advantage to have data centers in space?
And the advantage one is where I have some reservations as well, right? So, okay, some people say it is cold, right? It can be, but then you have a lot of thermal cycling. It does get very hot too when you're on the other side, right? You can get orbits positioned to maybe limit that. But at the same time, I think another benefit that I hear touted is the idea of offloading compute for a lot of the constellations that are in orbit. It saves you, and again, this isn't my specialty here, but it's what I've heard some customers say, it'll save you a certain X amount of time by not sending the data down to Earth to be processed, instead sending it to a satellite that might be somehow closer, right? And that's one of the areas I have reservations on. Like, is it really closer? But whatever. And that over, per satellite, per constellation ends up saving X amount of money per year, right? That's one area I've seen it touted. Another area is the amount of power that, with the emergence of AI on the ground, right? The sheer, I'd say, energy impact and ecological impact that AI, you probably heard a lot of stories recently, people talking about how much emissions it takes to run a chat GPT model or something. That's an area where I've seen a lot of arguments being made that putting them in space where you have access to that cheap solar power saves energy usage on the ground at the cost of, solving the other engineering challenges. That one could maybe, over time make sense, right? Like we're talking maybe like 10 years of development. Yeah, that might make sense. But I see use cases all around. I think the first step, though, is better compute on the individual satellites. And then the data centers, maybe they have a point, the ones looking at the data centers. I'm happy to make it possible because, that's good news for us. I just still have a lot to learn about how exactly they want to make that a economical benefit.
Yeah, I see that. Yeah, I mean, into this because it's a polymer and it's presumably it's lighter than a lot of other previous solutions. But is it more flexible? I mean, is it something that can be deployed in things like spacesuit design or things like that?
We are actually doing some work relating to the Artemis suits. So starting off right now on like some models right now, so simulations, preliminary work. One of the long-term things we're looking at, in addition to like panel inserts, like, basically imagine like armor, to be honest, is woven fabrics using this material that you basically extrude the filament to a much smaller diameter and use that to actually weave fabrics that are flexible, for them to have joints and so forth on astronauts. Now, compared to one thing to take into note, there are older materials that were investigated initially for shielding, but didn't see widespread adoption. An example is like polyethylene. Polyethylene is the plastic you see in plastic bags at a grocery store, right? It's a very common, I think the most commonly used plastic on Earth, maybe second. Polyethylene has a lot of hydrogen, has a good hydrogen content, right? Actually, I think the density of hydrogen is sufficient to give you better performance than water, actually, as a shield for protons, right? Like for some aspects of the heavy elements. But then it lags in other areas like electrons, I won't get into the physics there, but, certain amount of shielding of anything will solve your electron problem. But at thinner layers, this is relevant. Neutrons and the X-rays and gamma rays, that's where it's weak. So one other area where it is a little bit of a problem as well, that is honestly, I think the biggest problem with why it wasn't used is it has an extremely low melting point, like, usually like 85 C, right, 90 C, for some of the lower grades of polyethylene. And, how are we going to use it if it's constantly melting from thermocycling, right? Or if you're talking about these GPUs, they get hotter than, right? It's going to cause problems. So essentially what we did is we created a new polymer, right? And this was a lot of work here, right? This is a lot of material science that has equivalent hydrogen content, slightly improved than the polyethylene, right? But allows you to, have much wider thermal tolerances, much wider, right? So we can take significantly higher temperature, significantly lower temperature, right? Before getting brittle at the lower temperature, as an example. It's also a little stronger. And one of the most important facts is these other areas. So the electrons, neutrons, X-rays, and gamma rays, we have a significant advantage in just sheer shielding performance versus materials like that. That was made possible by the fact that our polymer was able to be doped, so adding additives into it, right, like the nanoparticles, without causing it to become very brittle, because that is another problem with other polymers, right? Some are much more conducive to additives, some are not, right? So from just the sheer, material to material comparison, that was one of the big advantages. But I think the integration with actual engineers was the key, making it easy to work with, right? Because I'd honestly would be willing to bet that even if our performance was 30%, 40% worse than it is, we'd still probably be able to, have made headway just because it's easy to integrate. You don't have to re-engineer your entire system to stick it into like if you have an aluminum enclosure, just slap it on top of it, you'll be fine. Like that's the kind of thing we want to make easy for the designers.
You mentioned 3D printing, so I presume it's a fairly specialized 3D printer, but nevertheless the polymer is 3D printable.
It is. So we actually, believe it or not, it's not as specialized as you would think. We do actually we got initially off the shelf 3D printers, like desktop grade 3D printers, like a MakerBot Method X, right? Modified it a little bit, right? This is back when we were at MIT, and then got it like through a lot of trial and error, got the settings to be able to print. Now we're using more sophisticated printers. We're testing out some large scale, like robotic arm printers that are capable of printing up to like, a few cubic meters. But the printing is what I was excited about it because with space, there's a lot of custom engineering still, right? It's not fully commoditized yet, even though people want it to be. It's coming, but it's not there yet. You still have a lot of systems that are wildly different than the next, even though they might be serving the same purpose, right? This is changing now that there's a lot of standardization approaching with the satellite buses. So instead of having to design a satellite from the ground up, you could just buy one off the shelf from one of the satellite manufacturers. But as it stood, we thought it was key to be able to have a scalable, customizable production option, right? And that's where the 3D printer came in. So that's what we focused on. But yeah, we have basically all it took was normal printers, some higher end printers, of course, nowadays, right? We use like $90,000 machines that are still, instead of having to be like, jury rigged, they actually have the capability to have like the tolerance on settings that we needed in terms of like thermal control and so forth. But yeah, it can work on a majority of FDM printers with some tweaking. Yeah. The other ways we do have other manufacturing techniques, like just normal injection molding, compression molding, and so forth. But the printing allows us to do a lot of unique geometries and solutions that weren't made possible otherwise.
Yeah, in terms of the work that you've been doing so far, like the SpaceX launch with NVIDIA, how closely do you work with companies like NVIDIA and SpaceX on those particular? Well, yeah, I mean, what companies are you working with, and how closely do you have to work with those companies to make headway and to prove out the product and show customers, what you're capable of?
So that's a very good question, because it actually, I think it's important for anyone looking at the space business in general, especially on like infrastructure, to take a lot of these things into account. To quickly answer the point of how closely we worked with NVIDIA, right? Because SpaceX, not really, right? They were just the launch provider here. Where we're still actually starting a dialogue with them now on like potentially shielding certain systems and so forth. But up until that point, I haven't really made a headway or didn't put an effort into going to guys like SpaceX, because, as a startup, you want to start with, SpaceX they have a certain style of integration, right? The way they work with vendors, the way they tend to like move is you need a little more infrastructure, at least I thought, before we started working with companies like SpaceX, right? We wanted to work more on the kind of small scale engineering proof points first, build up the trust, and then make our way into the mega constellations, if that makes sense, right? Yeah. But with NVIDIA, funny enough, we actually just bought the NVIDIA system off the shelf, right? And now we're in dialogue with NVIDIA, because of course they saw the launch and they're like, oh, wait, it's working, right? And yeah. So in general, though, to really make headway, though, we did have to do a lot of interfacing with the engineers at companies we work with. Companies like Starfish, Axiom, we're doing some work with Sierra, Moog, and so forth. But in the past, lots of startups. I started with the startups who are willing to take a risk, because they're like, oh, we want to do something disruptive. Let's take a look. Use that to build a few proof points. Then you start getting into making headway with the bigger guys, right? The bigger ones like who are dealing with extremely high risk missions or high profile missions, like Axiom with human spaceflight as one of their focuses. That's a huge bar for proof to be able to start getting into that space. So essentially what it is a lot of trial and error on showcasing, here's our data. Is this good enough? No? Okay, let's make it more robust. Let's do more tests. Let's more evaluations, right? Once you get into space the first time, that makes a huge difference. As you can imagine, now you've flown, people are much, much more willing to give you the benefit of the doubt. But initially it was an uphill battle because, you come in with a new satellite design, there's a lot of it's not that controversial. But if you come in talking about solving a problem that's been there since the dawn of the space age with a new material, when people are comfortable, everyone knows aluminum, right? Everyone is very comfortable with it. When you talk about replacing aluminum to some of these engineers, they're like, oh, come on, don't make my life harder, right? Let's hope it doesn't work, maybe in some cases. So there's a lot of proof when you're dealing with the fundamental technologies that you have to work your way up. It took a couple of years, to be honest, of just nonstop, trial and error with like communicating data, improving our data, getting more data, right? So it was extensively interpersonal, I'd say. Lots of discussions and back and forth with the customers we have.
Yeah, I mean, space is it seems to be a very conservative kind of place, because I guess it's so difficult and so expensive as well that you kind of have to be a little bit conservative. But then you see these big winners. Well, SpaceX is a classic example, isn't it? Where it's you try and topple it. And of course you have the 100 dead bodies of all the other people that tried the same thing, and
exactly.
and you get the odd Elon Musk who gets it over the other side. In terms of like the fun bit here is like, are we about to see an AI revolution in space like we've seen it on Earth in the last couple of years? Do you think AI is going to have, well, because of things like you're doing and maybe other people are doing as well, can you see like AI being that there'll be a lot of applications suddenly open that will be transformative? And if you can see that, what sort of things does that look like? What kind of things do we have to look forward to?
Okay, so absolutely, the answer is yes. Absolutely, right? I would even say that like after we showcased some of the results from the NVIDIA mission, right? There were some surprisingly large entities like prime contractors who all of a sudden were really seriously, it seemed, based on our work with them, putting that as a serious contender for an immediate product line, like using these AI enabled systems, right? What I think they're going to be used for initially is, of course, like I said, the optimizations on like, the image processing, situational awareness, is domain awareness, a huge area. But in terms of the capability, the average processing capabilities of our satellites, now that barrier is being lifted, right? We're going to see it integrated for everything you would see it integrated really in, not necessarily consumer goods on Earth, but cars, self-driving cars, automation and autonomous operation. That's the first area where I think it's going to make the most headway. So being able to do simple maneuvers without the need for like a mission control watching every single step, I think that's first, right? Collision avoidance, which is again becoming an increasingly annoying problem for operators. That's where that autonomous operation becomes critical, right? So what we're going to start seeing is a lot more basically space at first for the next couple of years. I think in terms of processing integration of modern AI systems, it's going to just catch up, right? Because we still need to catch up with what's on the ground. And then we're going to start to see the moves towards, sci-fi looking stuff with, spaceships that can move, very elegantly, land, take care of themselves, robotic systems that are able to manufacture or dock or, more just improvements all across the board in the general operation, right? Long-term disruptive stuff, however, I think deep space exploration is going to be a really interesting application there. That, I think there's still a little bit of a tiny bit of work to do, right? Just because when we're talking about, say, imagine, a fully autonomous but equally effective, rover, Mars rover, right? That'd be really interesting. Imagine the kind of science you could do. It's just nonstop, there's still a lot of autonomous integrations, of course, on, but being able to have some sort of decision-making capacity informed by like, an effective model, that would be interesting. So I think it's going to improve the science down the road, but right now it's just going to really improve the cost efficacy of everything in space dramatically.
Yeah, I mean, in terms of where you go next, what's the sort of next kind of project? Is
are there improvements to be made on the actual product itself, or is it it's kind of, you're kind of bound by the laws of physics, or are you actually able to sort of go, well, this is polymer version 1, but the laws of physics doesn't stop there?
Yeah. From a shielding perspective alone, we're pretty much at the laws of physics right now, coupled with our applied engineering, I'd say, because maybe, one day when you have metallic hydrogen that you can just layer on things, okay, maybe things will change. Right? But right now, realistically, we're at the kind of, we're at the ceiling with the pure shielding performance. However, what we're working on right now are basically extremely thin layers of metallic coatings over the material to give it the bulk properties of what you'd see on a metal, right? So think about these NVIDIA systems. The first step is making sure they work. But even when they're working in space, the next problem is the power usage, as I mentioned, like power generation. If you solve the power generation issue and you're running at the same speeds you run them on the ground, because usually when they send hardware into space, it's not just specialized. And if it's COTS, they're running it at a much lower kind of output, right? They're kind of throttling the system just because the thermals are a problem. You're in a vacuum. How do you radiate the heat, right? Once we start catching up in terms of the ability to use the system at its peak capacity, then the ideal case and what I think the market would receive now is having an all-in-one solution. So imagine 3D printing the entire satellite bus that can act as a thermal interface for your components on board because it has conductive properties in certain areas that are competitive with like copper or graphene even. And then in certain areas, you have the opposite, where you kind of want to have some essentially like heat shield-like abilities. 3D printing the entire thing, so there is no shielding layer, structural layer, thermal interface layer. That's kind of our goal, the long-term goal. The next step that's coming, though, is that thermal interface layer, making it so that it's making the plasteel part look more like steel visually, making it look a little cooler. It's going to look like a metal with the basically micron-thin layers of metallic additives. And one of the ideas is we're going to be drilling holes throughout the shield in certain areas. So now it's a heat or a thermal interface, right? That's our next step. A business next step, to be honest, is now that we've proven out we've had 3 now successful on-orbit missions, tons of terrestrial ones, is a little more productization. Now that we're slowly approaching the standardization, I'm trying to make it so that instead of all these custom enclosures, custom systems that we're engineering around, like when someone comes in with X and Y flight computer, when I look at all the customers coming in, they all have, their own mission parameters, et cetera, et cetera. But from a shielding perspective, it pretty much all lands in, as long as you're in LEO up to like 1,300 kilometers, you're going to have basically the same shielding requirement, right? When you get to GEO, it's basically the same requirement for the entirety of it, right? Mid-Earth orbit as well. So there's very clear discrete chunks that I could just group a standardized shield into, right? So one thing we're going to be doing now is working with some of the big guys, the big bus manufacturers, the satellite bus manufacturers, to have like standardized integrations with their satellites. So essentially, instead of having to come to us to custom shield a flight computer, you can just click the COTS compatible option on the bus manufacturer's brochure, right? Or website. But those are the immediate steps. And then there's the idea, which we are investigating, of chip level packaging. So actually, when you look at a board, right, and you see the little black squares, the integrated circuits, that black material is usually some sort of formaldehyde epoxy resin that just use it for some like thermal dissipation. We were saying if we've done some models here, we haven't built it yet, but if you replace the chip level packing, that little material, you can get the equivalent amount of shielding as what you'd have in maybe like a 15 to 20 millimeter thick shield packaged into the smallest form factor. And then you can start getting some crazy potential reliability figures or resilience. That still has a little bit of work to do, just because there's a lot of strategic partnerships that are necessary to be able to do stuff that you'd have to start at the fab for. But yeah, that's a little further down the road, but not too far. I'd say sometime in the next year we're going to look at that.
Yeah, so I mean, just to sum up, I mean, it does seem like a kind of, a paradigm shifting, or potentially a paradigm shifting product, in terms of it allows you to, it allows you to do more science in space. It allows you to do things faster. allows you to do things cheaper. It potentially opens up what I would consider my problem with things like Musk's got to get to Mars thing is when you look at how ill people are from spending 6 months on the International Space Station, and that's in a much lower radiation environment than you would experience on the trip to Mars. It seems that you have to crack the nut that you're cracking before you even really think about it, because it seems like it's almost a death sentence, or certainly a very horrible experience for an astronaut to spend 6 months going there, then landing on a planet, trying to sort out living there for a year and a half, and then making a 6 month journey back. Just seems to almost be preposterous when you think about the radiation risk. But it does seem that, you know, these kind of things actually give you a little bit of hope that maybe this is doable after all.
Exactly. And I totally agree kind of with your assessment there. And another thing that I think people need to remember when thinking about space is, you know, space, it's still very much so an applied science field. Like, you're really in terms of design, you have to take everything into account. It's not like, you know, just, to be honest, just, hammering together a new cabinet or something where, you know, you don't have to have a level of precision of 0.001, millimeters and so forth. And there's a lot of very smart people who have been laying down the foundation for decades, right? The reason certain things haven't happened isn't because no one thought about it, right? Like, the idea of using a larger rocket with, more payload space. Yeah, it's not like that's a physics or an engineering issue even. It's just a application of funds issue, right? So a lot of the problems that NASA has been very conservative on human space exploration, those are not unfounded, right? And the limitations, it's not the scientists or the engineers who are not just, being too slow, being overly conservative. They have a, scientific duty almost to make sure that this thing doesn't fail. And of course, they don't have the ability to just say like, oh, it failed, screw it, let's try again, right? Like the SpaceX approach. And, to that point, it's not, so this takes on one of those areas. The radiation thing, yeah, we can make it manageable, right? Now, what about all the other human factors, right? Psychologically too. That's the thing I think not a lot of people tend to think about. But again, it's going to be a long duration mission, right? It's never really been done before. If there's a slight chance of something going wrong, the comfort there. And then of course, like the logistics of, day-to-day interactions with other astronauts, making sure that it's, doable or livable, right? Not just doable, livable, right? Because the way I see it is people tend to, Mars is just there. It's not easy, right? It's not like Mars is an ideal planet, right? You could have Earth become like a nuclear hellhole, right? Like fallout, right?
Yeah.
It would be easier to live here by a long shot than it would be on Mars, right? Yeah. There's a lot of challenges. A lot of these things need to come together. And I see this as lessening one of those key areas, one of those fundamental environmental barriers.
Yeah. Before I let you go, I'll just ask one question that you kind of alluded it to really early on, and it's just come back into my head, and I know I'll get asked this, is when it comes to, obviously the way that we're shielding on Earth is Earth's magnetic field, and it kind of deflects the radiation that would potentially be harmful for us. So why is that not a sort of more pursued option when it comes to, basically magnetic shielding or using electromagnetic devices to shield yourself from radiation? Why is that not as also a viable solution?
For sure. So it's not just the Earth's magnetic field, right? And it doesn't necessarily always deflect particles. The northern lights are trapped charged particles that you're seeing getting pulled into the poles, right? It catches a lot of them, and in LEO, low Earth orbit, the protons that give us most headache are a lot of those trapped protons, right? So there's a physics thing, a physics understanding that we need to improve on, like how exactly do these charged particles interact with the magnetic field, right? Are we going to be, pulling some in, and is there going to have to be a way to dissipate that? Like maybe, I don't know, like turn it off every now and then, right? As an example, right? Yeah. There's models, like physics models that need to exist. And then on Earth, you also have the atmosphere. That does a huge amount. People, and it's very thick. You have miles of shielding, essentially, even though it's not that dense. It's huge, right? With the other problem, though, is the smaller magnetic fields gets to have the same strength, it takes exponentially more power, right? And the amount of power you would need to do to have a theoretical field that we think with our current physics would get the job done, which again, there's no consensus there yet, right? Is quite a bit. We do not have that capability yet. Do I think it'll happen? Absolutely. I think these some sort of active shielding is what they call it, right? That field is going to happen, but active shielding, I think, is like looking at AI technologies in the 40s, right? Like it's still quite a ways off. We're going to need several steps of infrastructure before we have that kind of miniaturized extreme power source and the ability to then deploy it in space, project that field, right? It'll happen. Physics-wise, it's not crazy, right? There's just still a few unknowns. I just like to say, with what we're doing, right? It's just like any engineering. It's not magic, and it's just a lot of clever application and maximizing the entire picture, right? Because that's, again, what space forces us to do, is look at a holistic picture. You could have the best shield in the world, but if it's hard to use, difficult to use, causes some supply chain risks, they're not going to use it, right? When everything is essentially mission critical, such a high risk environment, you have to really take into account these other factors, like the holistic factors, as well as the human factor of making it easier for the engineer who's already overworked to use your material, right? So I think that's really the key. With any space technology, that's really how you get things done. It's looking at the entire picture, not just maximizing the engineering side, looking at how it all fits together.
Yeah, it's even the culture, like you said,
exactly.
the culture has to be overcome as well. I think I have talked about it on the podcast before, the sort of radiation protection of computer electronics and just how old a lot of the electronics are on spacecraft. I mean, I remember it being something like it was the PlayStation 2 chip that seemed to be the most popular
that is.
chip, and it was at that point 20 years old, and it's it's in loads of these really posh satellites, and you think, God, isn't that crazy? Because I think a lot of people just assume that you find something cutting edge and you stick it on a spacecraft. Obviously, they're going to be using the latest computers. It's no, it just does. You kind of want it to be flight proven for a start off before you even try it on a critical mission. So, it's a really interesting subject, that kind of making things work in space. And it seems like you've got an amazing product and an amazing kind of the fact that you've got it into space and it's proving itself. That's really exciting. It's really exciting.
It is, and I appreciate that, because with space, it's easy to be proud of what you do, I will say, compared to prior startup experiences. It's like, oh well, we got into space a few times. It's not bad. Sometimes when you're worried about the general startup woes, you're like, well, at least I got that far. Yeah, exactly.
When you did get your stuff into space, did you actually go and see the launch?
I did. Yeah. So it was last May, I think it was May 21st, with Axiom Space, the SpaceX launch, where they sent up the Saudi astronauts, actually the first Saudi astronauts.
Oh, right,
Same flight, coincidentally. But I saw the launch, and I actually saw a return too.
Right.
Yeah, it was awesome. It's kind of so it went up, we ran to the other launch pad, just a bunch of us, and then you saw it land back. That was pretty cool. I didn't see the other two.
Thanks very much for coming on and chatting. That's awesome. Thank you very much.
Yeah, my pleasure. It was great, and thanks for having me.
You're listening to the Interplanetary Podcast, putting the ace back into space.
Well, there you have it. It's all those little tiny technologies that build up to make space travel possible. Which kind of makes me think, all this talk of going to Mars and things like that is just so improbable until we've got hundreds and hundreds of those types of technologies sorted. And they're all really, 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 really difficult. But anyway, good luck, everyone. Of course, that's what I want to see. But I'm just a little bit more dubious than most, having done this podcast for a while and learnt to be slightly more techno-unoptimistic. I think that's probably the thing that this podcast has taught me. Anyway, the other thing that this podcast has taught me is the generosity of just unbelievable human beings who have been on Patreon for a while now. And these human beings that have been supporting the show over on Patreon are Stuart Lawson, absolute legend, Ian Holland, Dr. Bob Hodges, Ben Guthrie, Jean Watchtanik, Tyrrell McAllister, Mark Schurn, Marissa Davis, Mark Huber, Kate Seal, Steve Croucher, Adam French, the glorious Jim King, and the lovely Mark Kelly. Thank you so much, everyone. Your generosity is nothing short of amazing. It amazes me every single month I have to announce your names. Thank you so much. And yes, if you want to join, you can come and join Patreon for free these days, or go up the pay scale and join Discord, etc., and join in with some fun. It'd be good to get some real opinions going back in the Discord, and maybe we can talk about them on another show. Until then, bye-bye, Spodcast!